Alright, hello and welcome back everybody. It's Thursday 4-9-2020. Okay, and today we're going to be talking about section 3.2. Okay, so this one's about polynomials. Okay, so we've already actually talked about polynomials a little bit, especially quadratic polynomials and linear polynomials. But a polynomial, at least the way this book defines it, is f of x equals a n x to the n plus a n minus 1 x to the n minus 1 plus a1x plus a0. Right, and this is really x to the 0, but any number to the 0 power is 0. Or is 1. Okay, so these are all called the coefficients, right? So this is like the a-n coefficient. And we call this one the leading term. A-n is the leading term if it's not 0, right? So or the leading coefficient. A-n x to the n is the leading term. A-n is called the leading coefficient. Alright, so here are some examples here. So we've already talked about, f of x equals a0. So that's a constant function. Like f of x equals 3. That's an example. We've also talked about linear functions. So you could have f of x be, 2x minus 1. Right, so this one, a0 would be -1 and a1 would be 2. We've also talked about quadratic functions last section. So that was, or last chapter actually. No, last section. So that would be like a2x squared plus a1x plus a0. So note, when we talked about linear functions, we instead of a1 and a0, we said mx plus b. But it doesn't really matter what you call those constants, right? So here they're writing it like this because they want to denote that this constant goes with this power, right? So for example, this is a quadratic. Function. And so you could have like f of x simply equal to x squared, right? That's where a2 would be 1, a1 would be 0, and a0 would be 0. Okay, so those are some examples. So we also talk about the degree of a polynomial. So this one has degree n, right? But that's kind of confusing because anyway. So like for example, a constant function would have degree 0 because the degree is like the highest the term with the highest exponent on the variable. So like this one is a degree 0 polynomial because it's constant and it's x to the 0 is the highest. This one, linear functions are degree 1 and quadratic functions are degree 2 and so on and so forth. Okay, so you can also have cubic, quartic, quintic, and it goes on forever. So in this book, you might see it defined differently, but in this book, one definition that they give a polynomial is that its domain must be negative infinity to infinity. So that means that all real numbers should be included. So like, so they give an example. So g of x equals 7x squared minus x plus 1 on 1 less than or equal to x less than or equal to 5. So in their definition, they say, well, it looks like a polynomial, but its domain, they give a domain that's not negative infinity to infinity. So they actually would say that this is, by their definition, not a polynomial. G is not a polynomial. But, I mean, you could also say, yes, G is a polynomial on this domain. Personally, I've never seen this definition, but since it's in the book, we're going to go with it. Okay, so just keep in mind that their definition of domain means negative infinity to infinity. Okay, 2. Their graphs are smooth and continuous. I don't know, something like that. But anyway, so what do smooth and what do continuous mean? Well, for just by looking at a picture of a graph, for example, you could have a polynomial. Polynomials always have smooth and continuous graphs. So this one, I'll draw 3 different graphs here. So and the last one I'll put down here. Okay, so these are all functions, graphs of functions, because they pass the vertical line test. But this one is a smooth and continuous function, graphical function, because, for example, it does not have a jump here. This is not a continuous. Continuous means that I can take my pencil and draw the graph of the function without picking it up and putting it down again. So this one, if I want to draw it, I have to draw this line, then I have to pick up my pencil and jump over down here. So that's what continuous, just by looking at a picture of a graph, kind of means. This one is also continuous because I can draw it without picking up my pencil. But look at these points here. So these are called. This one's a cusp and this one's a corner. It's a sharp turn. So that's kind of the definition of what smooth looks like on a graph. Okay, so polynomials all have this kind of graph shape. Okay, so by their definition, that's why this one wouldn't be a polynomial, because it just has these sudden stops and starts at 1 and 5. So those would be considered, cusps and or corners. Okay, but so let's see some other other common mistakes people make, in defining a polynomial. So we like, out of these couple examples here, if I give you f of x equals 5x to the 4th minus 2x plus 7, this one is a polynomial. By definition, right, of the book. So, but if I gave you h of x equal to x squared plus 1 over x minus 1, this one's not a polynomial. Because we can rewrite this as, you can break up the denominator as x squared over x minus 1 plus 1 over x minus 1. And these are fractions, and this one especially, you cannot, this one might break down into a polynomial itself, but it actually doesn't. You can't divide x squared by x minus 1. And this one has like an x to the negative 1 power in it, so this is not a polynomial. This is a rational expression, not a polynomial. Also, if you were to graph this function, you would have a discontinuity at 1, because if you plug in x equals 1, you'd be dividing by 0, and that's a no-no. So you'd have to pick up your pencil and skip 1 to graph it. Okay, so it's not a polynomial. So yeah, and then also that one that I showed you earlier with the weird, or the altered domain. That's, by definition in this book, not a polynomial. Okay, moving on. Right, moving on. So in our book, I don't know why they call it this, but this is actually incorrect to call it this, but I'm gonna just tell you guys what it's actually called. So this function, f of x equals some constant times x to the n is some power, a is some constant, is called a monomial. You know, monomial meaning it just has one term. Okay, so a constant function is a monomial. X squared is a monomial. 6x to the fifth is a monomial. You can make up infinitely many examples of a monomial. Okay, but in this book, and I'm guessing on the homework, they're called power functions. Okay, so I will refer to, I can use both monomial or power function, okay? So they like to talk about, you also want to notice that n would be the degree of your monomial or power function, and there's a difference between even and odd power functions. Okay, so for example, let's talk about even power functions. So if I have this graph here, 1, 1, 2, 2. Okay, if I have a graph here, a power function, you know, this power function doesn't have any, it's always going to be centered, you know, it doesn't have any translations, right? It's always going to be having a vertex at 0, 0, 0, the origin. So, like, for example, if I draw x squared, it looks, it's from last section we know that that's a parabola, right? So that's x squared. But the higher and higher your degree goes, the faster and faster your the skinnier or the faster your graph grows as x gets bigger, left and right? Because remember, if you have an even power, your number is always going to be positive. So even if I put in negative, sorry, these should be negatives. If I put in negative numbers, it's still going to give me a really big output, positive output. So, but take a look at, I actually drew these incorrectly. Let me redraw these. These here, actually, until you get to 1, are smaller than the x squared. Oops. Make sure I'm crossing there at 1. Right, so that's actually more. So the point to make here is that when you're in between 0 and 1, you have that x squared is bigger than x to the fourth, and it's, so I tried to illustrate that here in this picture, is bigger than x to the sixth, and that goes on. That's because, so think about it, if I had 1/2 squared, and I had 1/2 to the fourth and 1/2 to the sixth. Oh, not 1/6, 1/2 to the 6th. Which one of these numbers is going to be bigger? Well, if I use my exponent rule, if I have a fraction being raised to an exponent, I can write that as 1 squared over 2 squared, 1/4. Here I can write that as 1 over 16. And let's see, 2 to the 6th is 2, 4, 8, 16, 32, and 64. Right, so a 4th is bigger than a 16th, and a 16th is bigger than a 1/64th, right, and so forth. So that's why if you have some sort of fraction, this is going to be the case, right? If you're in between 0 and 1, if you have a positive fraction, that's going to be the case. Okay, so also, but if we're talking about x being greater than 1, if you have any number bigger, then it's the other way around. It's x squared is going to be less than x to the 4th, which is going to be less than x to the 6th, which is less than the rest of them, right? So that's like 2 squared, 2 to the 4th, 2 to the 6th, okay? So that's what we want to talk about with even power functions. And notice that as x goes to positive, as x gets bigger and bigger, the y value gets bigger and bigger, and as x gets smaller and smaller, or gets super negative, it's going to also just go to the same direction in the y direction. It's going to be going towards positive infinity in the y direction, as x goes to negative infinity in the x direction. Okay, so now we've talked a little bit about even power functions, so let's talk about odd power functions. So odd power functions so have some similar properties, but they also have some different ones. So if I draw that graph again, here's 0, 0. Here's 1, here's 2, 1, 2, negative 1, negative 2. Okay, so if the first odd function is just the straight y equals x. So that one right there. Okay, then the next one is y equals x cubed. So this one kind of comes down and goes up, and then just continues to go up like that. And then, but if you cube a negative number, it remains negative. So this one's going to kind of do the exact. It has origin symmetry. Remember we talked about that a little bit a couple sections ago. So this one would be y. So let's do one more. Let's do x to the 5th. So x to the 5th is going to be on negative 1, 1. It's going to be, or from 0 to 1, it's going to be a little bit smaller. But then after you get past 1, it increases faster, kind of like the even case. And it does a similar thing here. It decreases faster. Okay, so just like on the even functions, we have, if you're in between 0, if x is in between 0 and 1, x is bigger than x cubed, which is bigger than x to the 5th, which is same. And then once you're greater than 1, we get that the other relationship. Okay. So keep that in mind when we need to keep that in mind when we're talking about polynomials, is the behavior of independent monomials or power functions. Okay. So first let's talk about let's see. Right, so let's talk about, the book calls it end behavior. of polynomials. And what they really mean is like, as x gets really, really big, or goes to positive infinity, as it approaches its end of the domain, right, or negative infinity, what happens to the behavior of the function, right? So, so there's a couple different cases you could have here. So like, you could have a graph that looks like this. You know, a parabola looking, or an even function type graph, where this one, as, I'm going to introduce some notation here, as x, so this means as x goes to positive infinity, well, we look at the behavior of what the y, as we go further and further this way, the trend is that y is going up towards infinity. So this one would be f of x goes to positive infinity for this pick graph. So then we want to look at the other end as x goes to negative infinity. Our polynomial still is going up in the positive direction. So it's going to be f of x goes to infinity, positive infinity. Okay, you could have the exact opposite, a downward facing even function. So this one would be kind of the same here, but as x goes to positive infinity, as x gets bigger and bigger this way, our function is actually going down. So f of x goes to negative infinity. And as x goes to negative infinity, we get f of x going to negative infinity as well. All right. So so a couple more examples. You could have an odd function, so like x cubed. So in this one, you would get that as x goes to positive infinity, as we increase this way, f of x also goes to positive infinity. And this one, and as x goes to negative infinity, we see that our graph is going down in the y direction. So f of x goes to negative infinity, right? Because you can't really write equals here, right? Because you can never get to infinity, but you can write a goes to or an arrow. Okay, and if you had a picture like this, that's our last case. X goes to infinity, then f of x goes to negative infinity, x going to negative infinity, then f of x goes to positive infinity. So as we go this way in the x direction, y is going up. Okay. So let's do an actual example rather than just looking at these pictures. Okay, so this one asks. This one asks us. They give you this polynomial p of x equals 2x cubed plus 5x squared minus 7x plus 11. So first off, we know they want you to find the degree of this polynomial. So that's kind of easier because it doesn't require much work. You just have to find the biggest exponent. So this one has degree 3. So they say show that p of x, I don't know if you've ever seen that before, but a squiggly equal sign means approximately or behaves like 2x to the third as they say absolute value of x goes to infinity. So this is another way of saying as x goes to infinity and x goes to negative infinity. Because you could have, if the absolute value of x is positive, then it's positive x going to infinity. If the absolute value of x is, or if x is negative, then it's saying that x would be going to negative infinity. Okay, so just keep that in mind. So what we want to do is we want to rewrite p of x in a kind of silly way here. We're going to write it as 2x. We're going to leave that leading term alone, right? The term with the highest, with the exponent 3. We're going to leave that one alone. Always leave the highest degree one alone. But then we're going to do this. We're going to multiply this one by, it's going to be, so I'm going to rewrite this 5x squared in kind of a funny way. I'm going to rewrite it as 5x cubed times 1 over x, right? So that's, I could cancel out the one of the x's with the 1 over x and get back to x squared. So I'm really just multiplying by 1 there, and I'm going to do that with the rest of these terms to get an x cubed. So 7x cubed, and then this time I need a 1 over x squared to get back to 7x. And then this one I need an 11 times 1 over x. Sorry, I'm going to write this on the next line. Plus 11x cubed times 1 over x cubed. Okay, so now we've artificially installed a x cubed term in all 3 of these terms, or in all 4. So we're going to factor that out. So this is, we will factor it out of all of them. So we get an x cubed times, so if I factor it out of the first one, I get a 2 left over. If I factor it out of this one, I get a plus 5 over x minus 7 over x squared plus 11 over x cubed. Right. So now think about it. Now that I have it in this form, what happens as x gets super, super big? Well, x getting, and not thinking about this x squared term here a little bit. Let's just think about this one right here. As x gets really, really big, this one, 5 divided by a really, really big number, is just going to look more and more like 0 the bigger the number gets. Same with these two. This one's going to get closer and closer to, it's going to be a really, really small negative number. Or, I'm sorry, a negative number that gets really, really close to 0. Actually, even faster because we have x squared here. And this one's going to go to 0 the fastest because it's an x cubed term. So if you're dividing by a really, really big number, that just makes that number get closer, get smaller, and get, I should say this, get smaller and smaller in absolute value. Or in magnitude. Okay, so we can say as absolute x becomes large, this starts to look more and more like x cubed times 2 plus 0 minus 0 plus 0. Which now, if I distribute this out, equals 2x cubed. So that's how you would show what the function starts to look like after the absolute value of x gets really large, or as x goes to positive infinity and negative infinity. So we notice that that is precisely the leading term. So polynomials will take they look like their leading term as x gets really, really large. So as x gets really, really large, we can kind of disregard the lower order terms, the 5x squared, the minus 7x, and the plus 11. Okay, so if I gave another polynomial example, we could show using the same process that 4x cubed plus 2x squared plus 5x minus 17 approximately looks like 4x cubed as absolute x goes to infinity. Okay? Because 4x cubed is the leading term. Okay, I'm going to pause the video.